This is lecture 16.4, the ideal gas law. All right, so what we're going to do in this video, we're going to look, of course, first at the ideal gas equation. We're going to look at the mathematical form of that. It's something that's important that you're going to want to memorize. In the context of that, we specifically want to be informed about units. That's something we're going to need to take into account anytime we do ideal gas law calculations. We'll take a quick look at how we can use the ideal gas law to derive the simple gas laws, Boyle's law, Charles's law, Avogadro's law, all those other ones that we talked about in the previous videos, so that if you forget how to do those but you remember the ideal gas law, you can use that as a tool to go back and work on those as well. We're also going to look at the two most common types of ideal gas law problems that you come up with in quizzes and exams. One is where you have to solve for one missing variable. You've got pressure, volume, temperature, and number of moles. You know three of them, but you don't know the fourth, so you have to solve for that missing variable. That's a very common way for these to show up. And the trickier one, the more, I guess I'd say slightly more difficult, let's say more interesting, more fun types of problem are the ones where you have two states, something is moving from state 1 to state 2, and you use the ideal gas equation to figure out what the parameters are for state 2. Okay, let's take a look at all of those. All right, this is the ideal gas equation. It gives us the relationship between all of those four variables. When we looked at the simple gas laws, we were looking at relationships between pairs of variables. The ideal gas equation, though, gives us the relationship between all four of them, so that we can do calculations that involve all four variables. This is a really important equation. It's one of the ones you definitely need to memorize. One of the nice things about it is that it really kind of, the way it's written, it sort of rolls off the tongue. PV equals nRT. PV equals nRT. It just kind of flows, and that makes it easy to memorize because it's so easy to say. I was talking about this equation to a student one time, and he gave me kind of a funny look, and as I started to write it on the board, he said, "Oh, you mean PivNert." And so if remembering PivNert helps you, then that's fine. That's another good way to remember it. But regardless, however you remember it, as Brad Hamilton would tell us, learn it, know it, live it. Make sure you know this equation. It's important. All right, let's take a look at the ideal gas equation. I should have mentioned this on the last slide when I was introducing the equation. We have these four variables, pressure, volume, number of moles, and temperature, but we've also got this new one in here, this capital R, and this capital R is called the ideal gas constant. And R has the value of 0.08206, and then it has kind of weird units, which are liters times atmospheres divided by moles and kelvins. People often ask me if they need to memorize the ideal gas constant, and what I tell them is, no, you don't need to memorize it. I'll always give you that value on a quiz or an exam. If for some reason you have a quiz or exam and I haven't given you the ideal gas constant, then go ahead and raise your hand and ask for it. It just means that it was a mistake on my part. I'm happy to give you that number. If you are doing a take-home quiz or a take-home exam, then obviously feel free to go ahead and look it up. But the other thing that I tell people is, if you get to the quiz and you haven't already accidentally memorized the value of R, then you probably haven't done enough problems. Because when you get to the ideal gas equation, R is going to show up in I want to say almost, but I think I can say R will show up in every single calculation. And if R shows up in all of the calculations and you haven't memorized it by accident, just through sheer repetition, then you probably haven't done enough practice problems. All right. The other reason I wanted to talk about R is because this set of constants on R, or this set of units, I should say, on R, dictates the units that we need to use for everything else. So if we look at the other variables, this tells us that when we do calculations with the ideal gas equation, we need to make sure that our pressure is in atmospheres, our volume is in liter, the the amount of gas is in moles, and the temperature, as we said in one of the other videos, for temperature we always want to use absolute temperature, which means the temperature needs to be in kelvins. Okay. That means that you may need to do some kind of a unit conversion as part of the ideal gas law calculation. All right, another point kind of related to units is this concept of standard temperature and pressure, which is usually abbreviated STP. Standard temperature and pressure means temperature is 0 degrees Celsius or 273 degrees Kelvin, and the pressure is 1 atmosphere. So a lot of times problems will say, you know, how many grams of methane are in 1 liter at STP, or if 2.5 moles of oxygen is collected at STP, what will the volume be? So in those problems, it won't tell you the temperature or the pressure, and you're expected to know that STP refers to these two sets of conditions. Okay, all right, and this comes up quite a bit, so this is really very important. I see people all the time who get questions wrong on quizzes and exams just because they didn't remember the value of pressure and temperature at STP. So it's a simple thing to learn and memorize. Put it on a flashcard if you need to. Just make sure that you know STP. It's important. All right, so let's take a look at how we can use this ideal gas equation to derive the simple gas laws that we were using previously. Let's say we want to know Charles's law, which is the relationship between volume and temperature, and then again, this little sort of parenthetical statement when the other two variables are held constant. So what we're going to do is we're going to start with the ideal gas equation, PV equals nRT, and then we're going to go back to our definitions of direct proportionality and inverse proportionality, and we're going to try to rewrite that equation. I wrote the equation this way. I probably should have written this instead. We're going to try to rearrange PV equals nRT into a form that looks like this. But what I think I really should have said is a form that looks like this, or I should have said that, or a form that looks like that. Okay, and K, for this constant, I put K in these funny little brackets because K is going to be a little bit different here than it was previously. All right, so what we're going to do, we'll start with the ideal gas law. PV equals nRT, and we want a relationship between volume and temperature. So we want to isolate those two variables and put them as far apart as possible. Put one all by itself on the left, that's our Y, and put the other one all the way over on the right. Okay. Temperature is already on the right in this equation, so we'll just leave it over there. And so we want to isolate volume and make that the only value on the left. We can get volume by itself on the left if we divide both sides by P. So this means volume is nRT over P. And if we want to get temperature by itself, let's do this. Volume equals N R over P times T. Okay. Now, this R in this equation R is the ideal gas constant, so we know that R is a constant. Okay? But in Charles's law, when we're changing the volume and the temperature, the pressure and the number of moles of gas are also constant. So that means the N and the P are also constants. So if N is a constant, and R is a constant, and P is a constant, then this whole thing here is a new constant. We call it K prime or something. So this tells us volume is equal to K prime times T. And if that's our relationship, then this format, volume equals some constant times T, is direct proportionality. Ran out of room over there. And that means the relationship between volume and temperature is going to look like that, and our mathematical relationship between volume and temperature looks like that. Okay. All right, let's try another one. All right, let's try the same thing for Boyle's law, which is the relationship between pressure and volume. We'll start with PV equals nRT, and we're going to rearrange it to put one of our values, our Y value, as far as we can on the left, and the other value as far as we can on the right. Okay. So PV equals nRT. We want pressure on the left. It's already over there. We want to get volume on the right, so we need to divide both sides by volume. If we divide both sides by volume, we get P equals nRT over V. We want the V to be by itself, so let's just rewrite that. We're not really changing anything, we're just changing the way we're writing it. nRT times 1 over V. Okay. And now, just as before, R is the ideal gas constant. That's obviously a constant. Okay. And if temperature and moles of gas are held constant, then our T and our N are also constants. So that means this collection nRT is equal to a new constant, right? And so now we can write P equals that new constant K times 1 over V. And if P is equal to K times 1 over V, that is an example of inverse proportionality okay. And we know that the relationship between pressure and volume is going to look like that. Okay. And that's the equation that we can use to relate pressure and volume if we're just looking at those two pairs of variables, if it's just a simple gas law calculation. Okay, now like I said before, that's basically the same thing we did in the previous lecture. I just wanted to show you how you could get to the same point using the ideal gas equation. All right, so this is what a typical ideal gas law problem looks like. A steel cylinder contains 5.40 kilograms of nitrogen at a pressure of 1750 psi and a temperature of 25 degrees Celsius. What is the volume of the cylinder? Okay. So this is a typical gas cylinder. You have a lot of these in labs. Welders and things use them also for acetylene and things like that. We want to know what the volume is here. The other variables are given to us in the problem, and gauges here tell us what the pressure is inside the cylinder, and they can go up to a couple of thousand psi. These things actually hold a lot of gas and maintain very, very high pressures. Okay, let's take a look at what we need to do to solve this. All right. The first thing we have to do is be cognizant of our units. Okay? We can write down the variables that were given to us, but remember that we need to have our pressure in atmospheres, our volume in liters, amount of gas in moles, and our temperature in kelvins. So the first thing we have to do is a couple of unit conversions. Okay? So let's look at our pressure. We've got our pressure in psi. We need to get that into atmospheres so we can remember that there are 14.7 psi in 1 atmosphere. And when we do that math, we get 119.05 atmospheres, or 119 atmospheres. Volume, we don't have to worry about that right now because that's what we're looking for. So I put a little question mark there. The amount of gas, 5.4 kilograms. We need to get that into moles. So remember that 1 kilogram is 1,000 grams. Okay. And if this is nitrogen, remember nitrogen is diatomic. So if you look at the periodic table, you should be able to get the molar mass for N2. Nitrogen's 28.02 grams per mole. So let's add a second conversion step here. 28.02 grams per mole. Our grams cancel, and we're left with, let's see, 192.7 moles, which we probably want to round to 3 significant figures. We call that 193. And temperature, we need to put this into kelvins, so we will add 273, and that gives us 298 Kelvin. All right, so those are the values that we want to use in our calculation. All right, let's look at how to do the calculation next. All right, so I've gone ahead and changed the values of our variables here. I changed the units on these to atmospheres, moles, and kelvins. Okay. Then we just have to take the ideal gas equation and do a little bit of algebra. Right. We've got PV equals nRT. We're solving for volume, so we can divide both sides by P. Volume then is going to be nRT over P. And let me back up over here so I have a little bit more room. Volume is N, 193 moles, times R, the ideal gas constant, 0.08206 liters, atmospheres per mole Kelvin, times temperature, 298 Kelvin. Okay. And notice the temperature was given to us as 25 degrees Celsius, which looks like 2 sig figs. But once we add the 293 to it, to get 298 Kelvin, it's now 3 sig figs. So all of our data is in 3 sig figs. And that's all divided by the pressure, which is 119 atmospheres. All right. Then we check to make sure that our units cancel. Atmospheres in the denominator cancels with atmospheres in the numerator. Moles here cancels moles here. Kelvin here cancels Kelvin here. And we're left with liters. And that's what we expect. If there's one thing that I could encourage everyone to do, if there's one thing I could change about the world, it would be that everyone would put units in all of their calculations. I still make mistakes with my algebra here. It's a really, really easy thing to do. But if you make a mistake in your algebra and you don't include the units, you're going to get the answer wrong. If you make a mistake in your algebra and you include the units, then when you go back to cancel everything, you'll see, hey, wait a minute, my units aren't canceling properly. And anytime you got a mistake in the algebra, it will be revealed to you in your units. So please include all of your units in your calculations. That'll save you from making mistakes. All right. In this particular case, everything canceled out as we expected, and we got liters, which is what we want. That's good. And when we do the math, put all that into our calculators, we get 39.66 liters. And as I just said a minute ago, we've got 3 significant figures in all of our values. So the volume is 39.7 liters. All right. Let's try another one. All right. So here's a simple problem involving the involving STP and the ideal gas equation. How many molecules of gas are in 1 liter? I should say 1 liter of gas, probably be a little bit more clear, but how many molecules of gas are in 1 liter at standard temperature and pressure? Okay. All right. So we can start by writing down our variables, write down our equation, right? PV equals nRT, and our variables. And we see that the only value that's given to us is volume, which is 1 liter, right? We're trying to calculate the number of molecules, which is related to the number of moles. So N is our unknown. We can put a question mark next to that. Right? But they didn't give us the values for T or P. Okay? So they're expecting us to, I keep saying they. I'm the one who wrote this problem. So I am expecting you to have memorized the meaning of STP so that you know that STP means that the pressure is 1.00 atmospheres and the temperature is 273 Kelvin. Right? And that's the freezing point of water. People very often put in 298 Kelvin. In fact, sometimes if I'm not thinking clearly, I slip and start to write in 298 as well. Please remember that STP is 273 Kelvin, not 298. Okay, so now we want to know how many molecules there are. That means we're trying to solve for N. And if we've got PV equals nRT, we want to solve for N. We just divide both sides by RT, and that will give us N equals PV over RT. Right? So N is our pressure. One atmosphere times the volume, 1 liter, divided by R, 0.8206 liters, atmospheres per mole Kelvin, times the temperature, 273 Kelvin. Now, again, we put all of our units in here. Let's go make sure they cancel. Our kelvins cancel, our liters cancel, atmospheres cancel, and we end up with moles in the denominator of the denominator. And if something is in the denominator of the denominator, it moves up into the numerator. So put all these things in the calculator, and when you crunch the numbers, put all that in, hit the equal sign, you can get 0.04464 moles. Okay, our data are given to us in 3 sig figs, so we should round that to 3 sig figs. But of course the question is asking us for molecules and not moles. So we need to do one more step. We need to figure out how many molecules there are in 0.04464 moles. We'll need Avogadro's number for that. 0.04464 moles times Avogadro's number tells us that 1 mole has 6.02 times 10 to the 23rd of whatever those things are. In this case, molecules. So 6.02 times 10 to the 23rd molecules in a mole. And so cancel those out and put that in your calculator. You get 2.69 times 10 to the 22 molecules. All right, and that's our answer. Okay. Part of this was, there are a couple things here. One, remembering the ideal gas equation and doing the algebra to solve for what we're looking for. 2, remembering that STP means 1 atmosphere and 273 Kelvin. And then the last thing, in this particular case, we had to remember a conversion from first semester to convert moles into molecules. This Avogadro's number is important. Doesn't go away. So make sure you know that number. All right. Another common kind of problem that you get using the ideal gas law are these, as I call it, a two-state problem, where it describes the properties of a gas under state 1 and then describes the properties, or some of the properties of the gas under state 2, and it asks you to calculate something that you don't know for state 2. Okay, so here's an example. There's some organic matter at the bottom of a swamp which decays, releasing methane gas. The methane accumulates in the sediment until it escapes as a small bubble with a volume of 1.6 milliliters. The temperature at the bottom of the swamp is 8.1 degrees Celsius, and the pressure is 2.7 atmospheres. Pressure is always higher at depth underwater. How big will the bubble be when it reaches the surface, where the temperature is 28.5 degrees Celsius and the pressure is 1 atmosphere? All right, so we've got two different states, right? State 1 describes the bubble right here when it was released, and state 2 describes the bubble as it reaches the surface. Okay. We've got some, but not all, of the variables for all of these. What we're going to want to do on the next, in the next slide, we're going to identify state 1 variables and state 2 variables. But before we do that, we've said before we need to take account of units. So before we go to the next slide, and we've got this stuff right here, let's just go ahead and look at this. 1.6 milliliters. This is a simple conversion. We've done these before, so I'm not going to write out all the steps. You can work through this to check and make sure this is correct. But 1.6 milliliters is 0.0016 liters. Okay. We've got this temperature here. 8.1 degrees Celsius is, let's see, is 281.1 Kelvin, and 28.5 degrees Celsius is 301.2 0.5 Kelvin. All right, so we're going to look at all of our variables in the next slide. We're going to go ahead and put them in the right units before we worry about doing that. Okay, let's proceed. All right, so just as with the simple gas laws, we've got two ways that we can work through this. One is with a two-step solution, and one is by the other way is by isolation of constants. So let's go ahead and do this one both ways, and we're going to start with the two-step solution. And the first thing we have to do is collect our variables. So state 1 describes that bubble at the bottom of the swamp. We've got 3 of the 4 variables, but it didn't tell us anything about the number of moles. So n is a question mark. In state 2, as the bubble reaches the surface, we have information about 2 of the variables, but now there are 2 that we're missing, volume and number of moles. Okay. So we can't go directly to state 2 and do the calculation because we're missing 2 of the variables. Okay. But for our two-step solution, what we can do is first use the conditions of state 1 to determine the number of moles, and then once we have the number of moles calculated from state 1, we can move that down into state 2, and then we have enough to do the calculation of volume using the state 2 data. All right, so let's do this in a two-step method. Let's first solve for the number of moles. Okay. PV equals nRT. Therefore, N equals PV over RT, which is 2.7 atmospheres times the volume 0.0016 liters divided by R 0.08206 liters atmospheres per mole Kelvin, and our temperature, which is 281.1 Kelvin. Let's check our units. Atmospheres cancel, liters cancel, kelvins cancel, and we're left with moles. That's great. And if we put all of that into our calculator, we'll get 0.0000187 moles. And the pressure was given to us in 2 significant figures. The volume was given to us in 2 significant figures. So this number of moles is only good to 2 significant figures. All right. So this gives us, we'll put a 1 there. That gives us N1, which is that value there. Okay. Now let's use that to calculate the unknown variable, the volume, in state 2. All right. So we just went through this and looked at our state 1 variables. We calculated the volume as 0.000187 moles. So we can take that and we can now use that information here for N2, because the number of moles isn't changing, right? All the gas that's in the bubble stays in the bubble. It's like Vegas. What happens in the bubble stays in the bubble, right? So the number of moles isn't changing. That's a constant. Whatever we have in state 1 has got to be the same as it is for state 2. So now for state 2, we only have one unknown, and that's the volume. Start, as always, with ideal gas equation. PV equals nRT. To get volume, divide both sides by pressure. Okay. So volume is going to be nRT over P. and that is 0.0000187 moles, 0.08206 liters, atmospheres, moles, Kelvin, and T 301.5 Kelvin. Divide this whole thing by pressure, which in this case just happens to be 1. Right? All right. Let's check our units. Our moles cancel, our kelvins cancel, atmospheres cancel, and we're left with liters. Terrific. Put all of that in the calculator, and you get 0.00463 liters. Okay. A couple of things here. One is this the n that we calculated last time is only good to 2 sig figs, right? So we want to round things to 2 significant figures at the end. And also, if the question says what's the volume, this value right here is a volume, so that would be technically correct. But I think it's implied that if the initial information is given to you in milliliters, then probably the final volume should also be in milliliters. Okay. So let's just do that really quickly. 0.00463 liters times 1 liter contains 1,000 milliliters. This gives us 4.63 milliliters, and if we're rounding it to 2 significant figures, then our final answer should be 4.6 milliliters. All right, terrific. All right. Now, I like that as a solution method for this, because each time we're just using the ideal gas equation, we're just solving for one missing variable, and I think it's pretty simple to do it that way. That's the way I've usually done it. The textbook, a lot of times textbooks will do this using the isolation of constants method, and as I've said previously, the isolation of constants is actually a little bit more efficient. If you can get comfortable with it, it's a really nice way to approach these. So let's fairly quickly, let's go ahead and run through the same calculation using isolation of constants. All right, so let's take a crack at the same one using isolation of constants. We can start by recalling our state 1 and state 2 variables. And remember that the method of isolation of constants is that we're going to take our equation, in this case ideal gas equation, PV equals nRT, and we're going to put all of our variables, everything that's changing, on the left side, and we're going to put all of our constants on the right hand side. I think when we did this before, we always had only one constant, but now that we've got more things, we've got 4 different things we're juggling. What we find sometimes is that some of these, in PV equals nRT, R, of course, is a constant, but some of the things that are traditionally variables are also constants. In this particular case, as we said before, since the amount of gas in the bubble is not changing, the number of moles of gas is actually a constant. And so I've written this here. I've got state 1 variables. I've labeled this as N1, and for state 2 variables, I've labeled it as N2. But really, since that's the same, we don't really need a subscript on that. And we can just say the number of moles at the beginning in state 1 is N, and the number of moles at the end in state 2 is also N. The 1s and the 2s, the 2 subscripts, are not necessary. And number of moles is going to be a constant. Okay, so let's see how that works when we do the math here. All right, so we've got our variables here. We decided we're going to change n1 and n2 to just n, and we want to put our variables on the left and our constants on the right. So for state 1, we get P1 V1 equals N R T1, because P, V, and T are the things that are changing. N and R are both constants. And in state 2, we get P2 V2 equals N R times T2. We want to put the variables on the left. Since temperature is changing, that's a variable. We want to move that over to the left. In order to do that, we divide both sides by temperature, and that gives us P1 times V1 divided by T1 is equal to N times R. And for state 2, we get P2 times V2 over T2 is equal to N times R. And now, if N and R are both constants, then that whole thing is a constant. And if the thing on the left is equal to N times R and the thing on the right is equal to N times R, then those two things must be equal to each other. So that gives us the new relationship P1 V1 over T1 equals P2 V2 over T2. And that's the relationship we get between state 1 and state 2. Now all we got to do is rearrange that algebraically to solve for what we don't know. All right, so we just found that our relationship is P1 V1 over T1 equals P2 V2 over T2. V2 is what we don't know. That's what we're trying to solve for. Okay. And notice also, as happens with isolation of constants, our some of these things just drop away. The ideal gas constant disappeared, and N disappeared. So that simplifies things a little bit. All right, now if we want to get V2 by itself, we have to divide both sides by P2 and multiply both sides by T2. And so V2, actually let me go ahead and write it over here. Okay, so we will multiply both sides by T2, which puts a T2 in that numerator, and we will divide both sides, we got T1 here, divide both sides by P2, which puts a P2 in that denominator. So V2 is going to be P1 times V1 times T2 divided by T1 times P2. Okay. It's a little bit messy. I admit there's a lot of things to juggle around in this method. But it's kind of fun. If you like algebra, it's a hoot and a half, right? And a hoot is enough for anyone. A hoot and a half is just 50% bonus, right? All right. So P1, you got to be really careful with your 1s and your 2s when you do this. All right, so P1, that's our initial pressure, is 2.7 atmospheres. All right. V1, our initial volume, 0.0016 liters. T2, that's our final temperature, right? We had initial pressure and volume, but final temperature. Again, paying careful attention to the subscript 1s and subscript 2s. 301.5 Kelvin divided by T1, that's our initial temperature, 281.1 Kelvin, and our final pressure, which is 1 atmosphere. All right. Then, as always, we want to check our units. Our atmospheres cancel, our kelvins cancel, and we're left with liters. And when we run through the math and plug all of that into the calculator, you will be overjoyed. At least I was. Maybe you are mildly amused or merely content. I hope you're more than content. I hope you're at least somewhat amused to find that the result is 0.00463 liters, which is precisely the same thing we got with the two-step method. And when we convert that into milliliters and put it into significant figures, we get 4.6 milliliters, which is just what we got last time. Yay, fantastic. All right, great. There are tons and tons and tons of ideal gas law problems you can do. We've just done a handful here, but all of them pretty much follow the same steps, the same kind of procedures that we just did. So this ought to give you what you need to tackle all of the ideal gas law calculations. All right, so we've looked at the ideal gas equation. In looking at the ideal gas equation, we're specifically careful to look at our units, make sure we have everything in the right units, and use unit conversions when we need to. We talked a little bit about standard temperature and pressure, STP. That's something that you need to know. And make sure that you remember that STP is 1 atmosphere and 273, not 298, 273 Kelvin. And we also looked at how to use the ideal gas law to derive the simple gas laws. Then we looked at 2 different types of problems, solving for one missing variable, which is pretty simple. It's just, you just algebraically rearrange the ideal gas equation and solve for whichever one you don't know. The only trick there is to make sure you've got your units correct. And then we looked at 2-state problems, which are a little bit more complicated, and we solved that using either a 2-step method, which is simpler but a little bit longer, or the isolation of constants, which is a little bit more efficient but a little bit more, I won't say complicated. I'm trying to come up with a better word than that doesn't have a negative connotation. It's a little bit more involved, right? So you can use either of those, whichever of those you'd like better. That's what you need to be able to do for the ideal gas section of the course. Please practice those, look over homework problems, and let me know if you have any questions.